Hello, this is Stephanie Washer, and I'm going to talk about Module 4 from the Cengage MindTap Network Plus Guide to Networks. And this is for the RBC course, PCT 110, spring of 2024. So a couple of things I'm going to go over. I'm probably going to break this up into multiple sections where we talk about the TCP/IP core protocols. We'll use the layer 4, layer 3, layer 2 when we talk about the OSI model. That's what I mean by layers. So TCP and UDP are in the layer 4 for the OSI model. IP, ICMP are in layer 3 of the OSI model, and then the rest of these are layer 2. And then we'll talk about encryption protocols, remote access protocols, and troubleshooting and networking issues. I'm going to try and break it up into the least amount of video as possible, but I'm also trying not to keep the videos too long. So here's all of the items that we're going to talk about again, all the objectives. So describing the core TCP/IP protocols, how a TCP/IP message is formatted, using encryption protocols to secure network connections, configure remote access, and then employing TCP/IP for network discovery and troubleshooting. So this first video, we're going to talk about the OSI model layers. So we're going to go through layers 4, 3, and 2, transport layer, network, and data link. And then we're going to look at the different ports and protocols, the application encryption alternatives, common Ethernet switching features, network software and tools, and then general troubleshooting. So when we look at the TCP/IP protocols, we've got IPv4 and IPv6. So we've got TCP, UDP, ARP. There's so many others. The ones that we're going to talk about in this chapter are ICMP, IP, TCP, UDP, ARP, Ethernet, and one other that I can't remember off the top of my head. So we're going to talk about the different layers, how it puts headers and trailers on the information. So we're going to talk about how the information travels through the network at each layer. Just things to note, layer 4 is port addressing, layer 3 is IP addressing, and layer 2 is MAC addressing. So we'll look at that. And then if we look at, if for example, if you're at the browser and you are trying to request information from the web server, your payload goes through a process. So it gets broken up into different segments at the transport layer, and that transport layer puts a header on, which includes the port, source, and destination port. And then at the network layer, it is then turned into a packet because the network layer puts a header with the IP address, destination, and source IP address information in the beginning. And so you can see that each layer puts their own header on it. When it gets to the data link layer, it puts its own header using the destination and source MAC addresses in that header. And it also puts a trailer on, and then the physical layer will get it across to the other side. And then it does what de-encapsulates, and it goes back up the chain so the web server can look at the payload to answer whatever needs you have. De-encapsulates or decapsulates, either way, that's what happens. The other thing to note is switches look at the MAC address information, so they're at layer 2. Routers look at the IP addressing information, and they reside at layer 3. And firewalls work with ports and look at port addressing, and they're at layer 4. Now, a switch can be a layer 3 switch, and it'll look at IP addressing information, but for the most part, switches are looking at MAC addresses, and they're layer 2. So the first one, transmission control protocol, resides at layer 4. It is connection oriented, so it does a couple of things. So TCP makes sure that there is somebody on the other side before it makes any other communication. So it makes sure somebody's listening before it sends information. Sequencing and checksums. So TCP establishes the connection and transmits the actual data once the connection is established. So HTTP is an example of that. sequencing and checksums, it just makes sure the information gets to the other side in order, in correct order. So it's in the same order they were created. And then it makes sure that the information is all intact. Flow control, like whether somebody's talking too fast or talking too slow, you can, if somebody asks you, you can talk slower or talk faster based on their needs. So flow control is similar in that, based on how quickly the end or the recipient can accept data, so the other side. And so it takes care of all of this without us really even noticing. So what we look at here is the TCP header. We've got the source and destination port, sequence number, acknowledgement, the header length, reserved, and then we've got all of our our flags for the different parts of the three-way handshake or the parts of the sending the message. And then we have changing the sliding window size, the checksum, the urgent pointer options, padding, and then finally our data. All of the headers are grouped in 32 bits. And then each one of these, let's make this. We've got our source port is 16 bits, destination is 16 bits, and it just indicates the source port, and then the destination port. Sequence number identifies the data segment's position in the stream of data, so there is an actual number that corresponds to when it was broken up and then put into a sequence. The acknowledgement number confirms the receipt of data from the sender. The TCP header length, reserved, flags. The flags, these are the what you can look at when you're using Wireshark, and you can see what part of the exchange in the three-way handshake exchange it is in. So I'll just look quickly over here. Here is a screenshot from Wireshark where we can see the protocol. I mean, if you click on protocol, it sorts it by protocol so you can see which protocol you're using. And then you can look here and we can see which part of the three-way handshake we're looking at. And you can see all sorts of information. We can expand it and see more TCP information. And we can see destination port 443. 443 is a well-known number. It looks like the ports are here as well. So this one's a well-known port of HTTPS. And so there's different things that you can look at that give you information. And we also have the sliding window size, checksum, urgent pointer options, padding the actual data. So there's a lot of information. So here's the three-way handshake. So computer A is talking to B, which is probably a server. So computer A is like, hey, are you there? And then the server comes back and says, yeah, I'm here. And then computer, then it replies back with the information and establishes a connection. So that's all it does. And then the computer A, notice the sequence number here. This one is one higher. So every time it replies. So we've got sequence number and the acknowledgement. And then the sequence number, these two match. And then these two are in sequence. So you can see kind of how that goes. So we're kind of doing add one to the acknowledgement in sequence every time so this one adds one there, this one adds one there, and then we have our sequence number and acknowledgement values. Oh, and then this is our, we have our synchronized bit or synchronized flag or SYN flag, and then we have SYN and acknowledgements, and so we have the SYN and ACK flags coming back, and then we have our final acknowledgement. So, and then it goes through all of this and tells you exactly what I said already. So we're not going to worry about that too much. I'm not going to read through it. So a TCP IP header, here is everything in that TCP IP header. There's a lot. We've got our source, destination port. So this is a different example than we saw in the Wireshark. But we've got HTTP, which is 80. So well-known port 80. And then we're in the SYN acknowledgement, so we're in the second portion where the server is getting back to the computer. We can see that we have our different acknowledgements, and so our acknowledgement is set to 1 instead of 0, and the SYN is set to 1 instead of 0. You can see the size. And you can translate all of that field data using this table, and we already went through all of the different parts of a header, so you can look at that. Wireshark is a well-known protocol analyzer, and that it's really great. And you can, so this one just searches for not UDP, so it's TCP, but you can just let it go and it'll bring up everything, and then when you click on protocol it can sort it by TCP, but you can just have it search for TCP or certain protocols, search for ICMP. It's not just TCP, so you could have it do all sorts of different things. It's great. I used Wireshark at an organization I worked at, and that I couldn't figure out what computer was sending all sorts of data out. The ISP called me and said, if you don't figure out what's going on soon, I didn't realize, then we're going to shut your internet connection down. So I used to Wireshark and on the network, and I was able to figure out where so much traffic was coming from, and it was coming from one computer, and then I can unplug that computer from the network and then work on that computer to get it cleaned off. So the next one is UDP. So TCP is connection oriented, UDP is connectionless. So it's unreliable connectionless. TCP, reliable, connection oriented. UDP, unreliable connectionless. I can't tell you how many questions are on like Cisco exams or Network Plus or any kind of exams, and it's TCP and UDP, and it's simply them just trying to, have you understand that TCP is connection oriented and UDP is connectionless. So unreliable means exactly that. It does not guarantee delivery. It doesn't make sure that everything gets there in the end. So there's nothing that TCP does, UDP does. So we don't have acknowledgement of transmission, we don't have error checking, we don't have sequencing, we don't have flow control. But UDP is more efficient and is faster than TCP. So UDP, so like phone versus radio is what their example is. And radio, it sends out a signal no matter what, and it doesn't matter if the person's listening or not. So UDP is useful in a great volume of data, must be transferred quickly. So live audio and video transmissions over the internet. You can use it for DNS as well, but speed is more important than accuracy in some of these. So then, when we look at the UDP header, this is what it looks like. So this is UDP datagram. It's very, very simplistic, which is exactly why it's much more efficient and faster. Other protocols can work with UDP to kind of help with the reliability, and real-time transport protocol is one of them that can be used and is used to transmit audio and video. And it's at the application layer and helps with UDP on the transport side and make sure everything gets there. All right, so that is it for the TCP UDP video. The next video will be IP, Internet Protocol, and ICMP.